Hello, good evening. We're back to EASY lecture series. My name is Boris Jeremic. Today with me are Mr. Heshen Wang hi Heshen, and Dr. Han Yang, who is actually going to present today about energy dissipation, a little bit of theory of energy dissipation for interfaces, which are probably the most important energy dissipation locations in a soil structure system, soil rock structure system. So Han, please go ahead, share your screen. What I think we'll do is we'll try to shut down maybe our cameras. Heshen, you and me maybe should shut the cameras down, and only if you have questions, then we'll make it. Maybe I'll turn on my camera when I have questions, just to make sure that the internet is not breaking down. So I will stop my video, and Han, please go ahead.
Okay, can you see this, right?
Yes, we can see. Great. Yeah, go ahead.
Okay. Okay. Thank you, Professor Boris. So today we're going to continue our lecture series on the modeling of energy dissipation in earthquake solute structure interaction. So today we are going to be talking about the theory and formulation behind the modeling of energy dissipation for the interface element between the foundation and the soil. So here's an outline of our entire series. So today we're going to talk about the plastic energy dissipation in those interface elements. So again, we're going to start from the energy balance in a dynamic inelastic system. Been using for the solids and also the structural elements, and now we're going to use the same thing for the interface elements, just to keep it consistent for the whole system. So we'll again start from the equation of motion in its global incremental form. So this is the equation of motion here, and then from there we can derive the energy balance equation here, global rate form of the energy balance equation. So we have talked about this before, so I'm not going to go into much detail here. But the point is that we have identified all the energy forms here in our system. So from left to right, we have the kinetic energy, we have the energy dissipation due to viscous damping, then we have the plastic energy dissipation term, plastic free energy, and the strain energy or the elastic free energy. And according to energy balance, all of them add up to the input energy into the system. So next, we're going to move on to the material level to determine the plastic energy dissipation that is happening in the material. So we're going to use the same thermomechanical framework. Again, we have been using this for our inelastic solids and inelastic structural elements. So here we're going to use the same thing for the foundation and soil interface elements. So here we have the rate of plastic energy dissipation. Here we say that the rate of plastic energy dissipation equals to the first term is the material work, which is the stress multiplied with the rate of the strain tensor, minus the second term here is the rate of the elastic strain energy, which is the strain tensor multiplied with the incremental elastic strain tensor, and then minus the third term here, which is the plastic free energy density. And we say that the plastic dissipation density should always be non-negative. Now this equation contains the two very important, the two principles of thermodynamics. So the first law of thermodynamics says that the stress power that is input into a material body by external loading is transformed into elastic strain energy, plastic free energy, and plastic dissipation. And all of those forms of energy must be considered to maintain the energy balance of the material body. That's the first law. And then the second law of thermodynamics says that the rate of change of plastic dissipation should always be non-negative at any given time. Now, at this point, we have highlighted many times because it is very, very important, and it is one thing that we can always check if your calculation of energy dissipation makes sense or not. Yeah, so those are the two laws of thermodynamics. So next, we're gonna move on to talk about a little bit details of the modeling of the soil foundation interface. So this is the contact interface between your foundation and the underlying soil. So you can have different type of foundation, no matter what the material is. You're always gonna have an interface or a special kind of material layer between the foundation and the soil. The behavior of this soil foundation interface is significantly different than the rest of the underlying soil. So that's why we need to model it specifically. And also, because of the earthquake shaking, you can potentially have the detach of the foundation and soil, or when they are made into contact. So here is a simple plot that illustrates this process. So maybe at the beginning, you can have a little bit of gap between the foundation and the soil. So at this time, there's nothing happening between them. There's no interreaction. But then later, when maybe some certain type of load is applied, then they can be made into contact, and then there'll be interreaction in the normal direction and in the shear direction. Yes, please.
So that gap, you usually have self-weight. So usually there's really no gap. I mean, gap maybe if you have some shaking and things start to lift up. But what I wanted to say actually is more, this actually same theory, the same story applies to all sorts of joints and interfaces and contacts in civil structures or any other mechanical systems. So for example, for dams, you have joints between different blocks of the concrete dam that are usually grouted, but sometimes they can open and they can slip. If you have different contacts in interfaces in the concrete structure, you know, in rock mechanics, you have all these blocks of rock and they're all connected with some cracks, some joints. This same theory applies exactly there too.
Yeah, yes, that's right. So yeah, so here we are calling it the interface, so sort of to keep it as a general name, so it can be also used for different other types of interface between other kind of materials and elements.
Yes.
So in terms of the implication of this element towards energy dissipation is that in a soil structure interaction system, the soil foundation interface is a very important source of plastic energy dissipation. Now, the main reason behind that is that when a soil structure system is loaded, especially when it's loaded with seismic loading, it's going to be, there's a lot of cycles going back and forth. So as you can imagine, there's going to be a lot of potentially gap opening and closing. So that creates a lot of potential for energy dissipation. And also there's can be the frictional slipping happening between the foundation and the soil in the shear direction. So those are the main reasons why it's a very important source for plastic energy dissipation. So it not only does this behavior changes the energy dissipation in the system, but also controls the overall response of your system. So it's a very important component that we should carefully model. So the way we are modeling is that we are using so-called a sort of a penalty method that for the normal direction, the stiffness or the force will increase significantly when the two parts are made into contact. But in the really interesting part that is related to energy dissipation happens in the shear direction because we model the interface element behavior as inelastic in the shear direction. So this is where the energy dissipation happens. So it's only in the shear direction. And to model the shear behavior, we have basically 3 material models. So starting from the most basic one to a little bit more sophisticated, more realistic, and then the most sophisticated one. So now I will start to discuss briefly about these 3 models and how much difference there is in the calculation of energy dissipation for all 3 of them. So first we have the elastic perfectly plastic shear model, or EPPS model. So these 4 plots shows the material behavior. As you can see, for the monotonic behavior, this is a very typical more column type of response. So first we have a linear elastic stage, and then after the material yields, it just has a constant shear stress. So, and similarly, when you have unloading, loading, and then cyclic loading, so these are the behaviors of this material model. So this is the yield function. As I mentioned before, it's a typical Moore column type. Here is the yield function. The one thing to point out is that, as you can see, it's a combination of basically the shear behavior in the two directions. So because when you have a fully 3D model, you have one normal direction between the two surfaces, and also you have two shear directions that are perpendicular to each other in on the interface. So here is the yield function. As we can see here, there is no internal variable, which means there's no hardening or softening that's happening in this model. So if you remember earlier in our earlier lectures, we have established that the plastic free energy is physically, it is related to the evolution of the material microstructure, and the microstructure of your material is usually modeled as the evolution of the internal variables or the hardening and softening laws. So in this particular model, we assume that there's no internal variable, there's no hardening or softening. So that means there's no evolution of plastic free energy for this model. So that also means that all the and how good it is will depend on the specific type of loading and material that you have. And later, for more sophisticated part. Yeah, please.
I lost sound as soon as you started talking about the really important part, because there's no evolution of plastic free energy. The sound got lost, so please repeat that.
Okay, so yeah, so the point for this model is that so there's no internal variable, there's no hardening or softening, and the important part is that we have established that the plastic free energy is physically related to the evolution of the microstructure of your material, and that is modeled by the internal variables or by the hardening and softening laws. So that means when you have no internal variable in the model, there's no evolution of plastic free energy. That also means that all the plastic work will become the plastic energy dissipation for this specific model.
Yes.
Right. Okay, so next we move on to the second model that is a little bit more sophisticated compared to the previous ones. So here we have the nonlinear hardening shear model, or NLHS model. So here is the material behavior for this model. As we can see that now the overall behavior is nonlinear, and there is a hardening law involved in here. So this is the unloading, reloading behavior. This is the full cyclic behavior of the model. So here is the yield function. So the only difference, if you compare this one with the previous one, as you can see here, in this term, we have the so-called residual friction coefficient, and this is the constant number that does not evolve with the material. But here in the second model, we have the internal variable, which is the back stress here. Obviously, because again, we have the two shear directions, so we have two back stress internal variables, or you can think about as the two components of the back stress in the two directions. So the evolution of those back stresses are controlled by the hardening law here. Here we are using the Armstrong-Frederick type of kinematic hardening here. If you remember in our previous lectures, we also used this very similar type of formulation for the inelastic solids. So later we will also see that the energy calculation for this type of material is also very similar to those we have used for the inelastic solids, because the formulation of the model itself is very similar. So here, the main difference for energy in this model is that now we have the actual internal variable, which is the back stress. So the evolution of the plastic free energy is actually happening for this model. And that also means that only part of the plastic work becomes the plastic energy dissipation. The third model we have is one step further, like a little bit more, even more sophisticated compared to the previous two models. So here we have the nonlinear hardening and softening shear model, or NLHSS model. So here is the material response. As we can see, the main difference here that we have actually plateau for the shear stress or the normalized shear stress. So as you can see, after the peak, there's going to be a softening branch. So this is the main difference of this model compared to the previous two. So again, uh, before the peak, the yield function, the yield function for this model is exactly the same. The hardening law before the peak is also the same as in the previous one, but now we add a after peak softening branch. Excuse me. So the softening law here is defined by those two equations and the two material constants that's related to the softening rate and the size of the peak plateau. So again, I'm not gonna go into more detail about this model itself, but the implication of this model in terms of the energy dissipation is very similar to the previous one, which is that now there is a internal variable, so there is an evolution of plastic free energy. So again, only part of the plastic work will become the plastic free energy, the plastic energy dissipation. Okay, so now we have discussed the three different types of material models, so we can show the equation of plastic energy dissipation in the interface elements. So first, we have the plastic free energy in the incremental form. So this is the equation for that. As you can see, the plastic free energy is indeed related to the internal variables, which is the back stress or the two components of the back stress for those models. This form, this plastic free energy, the form of this equation, if we compare this one with the one we use for the inelastic solids, we can see that it is very similar. So again, this is because the formulation we use for the model itself is very similar. So after we got the again, it's in the incremental form. So we say that incremental plastic energy dissipation equals to this first term in the brackets is the plastic work, because as you can here, it's the multiplication between the shear stress and the incremental plastic shear strain. And then minus the second part is the plastic free energy. So this is the approach we have always been using to calculate plastic energy dissipation. So again, after this subtraction, the plastic energy dissipation should always be non-negative to satisfy the second law of thermodynamics. So here are just some of the reference that I use for the interface material model itself, and also the energy calculation for the interface material. So if you're interested, please go and look up more details. So here are the acknowledgements. I'd like to thank the collaborators and the funding sources, and for more information of the contact interface and the energy calculation, please go to the website of the real simulator. They're all implemented there, and there's documentation. And with that, thank you.
Thank you very much. So thank you very much. This was very interesting. So, you know, one of the claims of some of our senior colleagues, can you get out of the share screen?
Yes.
One of the claims of lots of my senior colleagues is that most of the energy dissipation happens in that interface zone, however thick, however thin. That one guy, famous guy, Bob Kennedy, claimed that that's about a foot, 20 to 30 centimeters zone where this slip happens, maybe less, maybe a little more, depends on the shape and how rough the foundation is. But this is seriously, this is certainly the case. And we'll continue with these lectures, and I think you're also going to show some examples a few lectures down the road, but I think we're going to continue with the viscous damping and so on.
Yes.
And the numerical damping maybe next time, and then we're going to go through some examples. Thank you very much. Good evening, good night to everybody. It's 8:39, 8:40 in Switzerland, it's 11:40. It's not even noon yet in
11:40.
Davis. Okay.
Almost noon. Yeah.
Almost noon. Okay. Well, have a good lunch. I'm done with
A
my
good
dinner,
lunch.
so
Exactly.
thank you very much. So I'll stop recording now. Thank you.